Have you ever clicked on something in an app and then nothing? The whole thing just freezes up. Yeah, we've all been there, staring at that frustrating little spinning wheel. Well, that's often just a symptom of a much deeper issue. And today, we're diving into the solution, Java multithreading. This is the powerful concept that turns those frozen, clunky apps into the super smooth, responsive experiences we all expect.
So, to really get why multithreading is so cool, we first have to talk about a problem that has probably driven you crazy more times than you can count. It's something I like to call the one-track mind problem.
Oh, you know the feeling. You click a button to download a big file or maybe to process an image, and then bam, the entire app just locks up. The cursor starts spinning and you can't click on any other buttons, you can't scroll, you can't do anything. That right there is the classic sign of a single-threaded app, and it's basically trying and failing to do two things at once.
Let's think of it this way. Imagine a kitchen, but with only one cook. Now, if that cook is busy chopping vegetables and it's a 10-minute job, they can't also be stirring the soup on the stove or checking on the roast in the oven. Everything else just has to wait. That's your single-threaded program. It can only handle one task at a time, and if that task takes a while, the whole kitchen, your entire app, just grinds to a halt.
So what's the fix? How do we get that soup stirred while the veggies are being chopped? Well, the answer's pretty obvious when you think about it. You hire more cooks. And in the world of programming, that solution, our multitasking hero, is multithreading.
So what exactly is multithreading? Well, it's really just a way of executing multiple, separate parts of the same program at the exact same time. Back in our kitchen, this is like having a whole team of cooks working together. One is handling the chopping, another is stirring the soup, and a third is managing the oven. They're all working in parallel at the same time.
And the advantages here are huge. First, you save a ton of time, obviously. But second, and this is really important, if one cook or one thread makes a mistake, like dropping a bowl of ingredients, the others can just keep on working. That independence is what makes apps robust. And finally, they're all sharing the same kitchen resources, the CPU, the memory, which makes the whole operation incredibly efficient.
Okay, so we've got our team of cooks, our worker threads, but what's their life actually like? What's the journey of a single thread from the moment it's created to the moment its job is done? Let's take a look.
Turns out every single thread goes through these 5 distinct stages. First, it's new. It's just been created, but it's not doing anything yet. Then it becomes runnable. It's ready to go, just waiting in line for its turn with the CPU. Once it gets that turn, it's running. It's actively doing its job. Now, sometimes it might have to pause, maybe wait for a download to finish. That's the waiting state. And finally, once its task is all done, it enters the dead state. It's a pretty straightforward life cycle.
So we get what a thread is and the life it leads, but as programmers, how do we actually, create these things and give them their jobs to do?
In Java, you've basically got two main options. The first is extending the thread class. You can think of this as hiring a full-time specialist cook. The second way is to implement something called the runnable interface. This is more like hiring a freelance contractor for a specific gig. Now, the runnable way is often a lot more flexible, but honestly, both methods get the job done.
Now listen up, because this part is absolutely crucial. No matter how you create the thread, its instructions, its recipe, if you will, always go inside a method called run. But, and this is a big but, you never ever call run directly. You call the start method. See, calling start tells Java, hey, create a brand new thread and have it execute the run method. If you call run yourself, you're just doing the work on the main thread, and you don't get any multitasking at all.
And when you do it right, you see something like this. Notice how the output from the main thread and the child thread is all mixed up and jumbled? That's not an error. That is the whole point. It's proof that they're running at the same time, and the CPU is switching between them so fast you can't predict the order. If you ran this again, you'd get a totally different mix. That beautiful, unpredictable chaos is the very essence of concurrency.
Okay, so having all these cooks working at once is incredibly powerful. But as you can probably imagine, it can also get pretty chaotic. If you don't have some rules in place, they're just going to start bumping into each other and making a huge mess.
And that brings us to the fundamental challenge here. What happens when two of our cooks need to use that one special stove at the exact same time? Or, in our world, what if two threads try to write to the same file or change the same variable simultaneously? Well, you get a disaster. Your data gets corrupted, and your results are completely unpredictable.
The solution is a little thing called synchronization, and it's basically like putting a lock on that stove. When one cook needs to use it, they lock it. Any other cook who comes along has to wait until the first one is finished and unlocks it. In Java, this makes sure that any shared resource can only be used by one thread at a time. It prevents the chaos and keeps all your data safe.
Okay, so we've stopped our cooks from crashing into each other. That's great, but what if they actually need to coordinate? What if one cook finishes chopping the vegetables and needs to tell the other cook, hey, it's time to add these to the soup?
This is where interthread communication comes in. Java gives us these cool methods called wait and notify. This lets one thread basically pause itself and say, okay, I'm going to wait right here until I get a signal. Then another thread can finish its job and send that signal using notify to wake the first one up. The perfect example is a bank account. A withdraw thread might have to wait, if there isn't enough money, until a deposit thread runs, adds cash, and notifies it that the funds are finally available.
So let's bring all this together. Let's step back from the code and the kitchen analogies and see how this one concept is the engine that powers the technology we use every single day. Because this isn't just some abstract theory, it's everywhere.
I mean, really think about it. That silky smooth user interface on your phone, that's one thread listening to your taps and swipes, while other threads are busy downloading data in the background. High-performance video games, they use different threads for graphics, for physics, for enemy AI. Those giant web servers that handle thousands of users at once, you guessed it, they give each user their own thread. Multi-threading is, quite literally, running your world.
And this brings us back to another critical benefit, stability. Because all these threads are independent, it makes our software so much more robust. If one little part of an app crashes, kind of like when a single tab freezes in your web browser, it doesn't have to bring down the whole program. A single failing thread won't stop the others from doing their jobs.
So we've gone from a single lonely cook to a whole team working in perfect harmony. But our kitchens, our computer processors, they're just getting bigger and bigger, with more and more cores every year. It really leaves us with a fascinating question to think about. As we get even more of this power to run things in parallel, what new kinds of complex problems are we going to solve next? The future is, without a doubt, multi-threaded.